Okay, I think I'll start. And since we are going to go over the discussion first, it's probably a good time to wait, like if anyone's going to join in. Mostly how I'm setting up the class today, it's going to be first like, discussion on readings. I'm assuming like up to half hour maximum. We can have a short discussion depending on the complexity, we can increase it. But then I want to introduce to them to some basic concepts of machine learning. Then I'll describe the pipeline of you start with gathering the data and then you evaluate a model. Then we'll go over different phases of that pipeline one by one. So today it would be conceptual without any data set. Thursday it would be coding. So I'll go over some toy data set and we'll actually go through the process. And the assignments associated with these things are going to be basically simple notebooks where you'll have half of the problem and you just have to fill in the remaining portion. I mean, so don't expect them to be like undergrad class assignments. These are grad class assignments, so they are very, you have to put in some time, but not a lot more time, because I want to focus on readings and discussions every Tuesday, so that we have this new space of AI for social good, which keeps on growing while you're also learning how to implement it. So both things should go on together. So before starting the discussion, there was a discussion on Thursday, and there were a few active participants, and I want to just in general ask, like, how do you feel about the discussions in the class? And is there a particular way you would want me to conduct those? Like, should those be student-led, that every week one student will present a paper? Many special topics classes are like that. But the downside of it is that we want to cover a lot more technical content also. So it's not equally practical to do that. But if you're interested, I can do something like someone can volunteer for a particular reading. We can go over it. Any suggestions?
And discussion Tuesdays will be primarily discussing readings.
Yeah.
I prefer multi-people.
I figured you missed me. Sorry.
Well, we could post discussion questions on Piazza.
Yes.
And like maybe like for Monday night, and then we could all read each other's discussion questions and like be ready to respond to them. That could be like a jumping off point for class discussions.
That might be a good approach, because I wanted to do the discussion anyway after the class. So my idea going into that was that we first do like sort of a discussion in the class. So we go over the paper. If everyone hasn't really gone through the details, we go over that, and then we can follow up on a discussion. But maybe starting the discussion on Monday is actually good. So on Piazza, you can start putting in comments or questions. Tuesday coming into the class, we'll go over some of those, some more points that emerge. And by the end of Tuesday, basically, Piazza communication can settle in. And the assignments, originally the way I planned them is that I'll assign them somewhere on Tuesday night or Wednesday, and they'll be due the following Tuesday. Is that sufficient enough time, or sufficient enough? Students who are not enrolled are not really obliged to complete the assignments, but if you want, you can. Okay. So, there's a Piazza link. So anyone who wants to join the Piazza, on the course website, you can just click the link and get yourself added to Piazza.
Yeah, so I haven't really used Piazza for like long discussions. But I guess we could just have like a note for before class.
Yes, so exactly. So what I'll do is every Monday I'll put up maybe like n number of posts, and being the number of readings that were assigned, and then underneath each post you can just create a thread of posts going on. Yeah, so because there is an option of discussions on Canvas, but then I don't know, it's not as friendly. So in terms of usage, Piazza is probably good. Like we can have questions over there, and we can have all the follow-up on the topics.
I think that'd be good for like more technical questions.
Yeah, for technical, that's the main platform you're going to use anyway. Piazza. Okay, so I'll start with the discussion. Should I initiate it, or I mean, anyone would like to jump in and actually start discussion on one of the papers. The primary paper that I want to go over is obviously the one that I closed with last night on Thursday. The McKinsey. Sorry. I had no idea that this wasn't connected. So if anyone is on streaming, it's on, but the video is in.
Why don't you start just so that you can feel for how you want the other papers in the future to be discussed? Like
Right.
what things are most important to you, and then we can always get feedback to you.
All right. So I'll cover the McKinsey paper. I'm assuming everyone has gone through the paper, at least in somewhat detail. So the idea is that they want to build this platform where people in production level domains, people who actually work on things in social good, people, companies which are involved in artificial intelligence, how can they actually find common ground and build on this process, right? So in order to do that, they have actually defined a very good set of AI. Let me open the paper and go over it. Yeah, so the first part that they have done is mapping AI use cases to domains of social good. The idea behind this is there's so much that can be done in social good, right? Society faces different challenges, and there are several applications of artificial intelligence that are already known. There are ways in which we know how to proceed. So can we actually center to some concrete domains which are more reasonable when we start to think about this entire process of applying artificial intelligence and machine learning for social good? The space is too wide and abstract. How do we center it down to practical domains where the idea is to be able to replicate things that are already known. So if you found a solution that worked well in medical imaging, can you really use it on multiple other things that are somewhere similar? So joining them in different spaces together, putting them in verticals, it makes it easy because now you have sort of defined values and you're seeing, oh, this application works across health and healthcare. Can it work on different applications of healthcare? So boiling down a very large space into 10 particular AI potential ranges. So anyone would want to pick a particular one if they found something to be interesting?
Just which area we find interesting, or
Yes.
the area that.
Mhm.
I mean, I think even related to the other paper on Google, TensorFlow usage in medical imaging, I think it's a health area right for AI, just because you have a lot of use cases and it's helpful to prioritize.
Exactly.
So I really like that breakdown.
Yeah.
And you already have a lot of really technically able people do that already, so training them on like components of artificial intelligence is like, there's probably less of a
Mhm.
barrier.
Another thing significant in healthcare compared to anything else, maybe public and social sector also have a win in that case, is the availability of data. So processes, even without machine learning, the way they were approaching these things like since 20, 30 years, they have been collecting a lot of data which is organized. So if a person without much background in without much background in healthcare goes on to look at these problems, they have data that they understand. They have data in the structure that they understand. That helps two domains basically collaborate on one problem. That I don't know much about healthcare. So if I'm collaborating with someone who is an expert in healthcare and I want to do the machine learning part, we have to find some common language, right? I think that approach is so far easiest in health and public sector because of the organization of data. So if you look at World Bank, they have provided large amount of data sets, and those data sets look very similar to any Kaggle challenge data set. So Kaggle is one of the big repositories for machine learning challenge data sets. They keep on hosting new challenges, which are sponsored by some companies or organizations. And it ends up in resulting in a big base for data sets to learn machine learning with or just test around, right? So how they structure them is in a columnar fashion. So it's generally a CSV, and while those data sets contain more concrete information and somewhat are engineered to the feature selection side, these might be just raw samples of data. But one thing which is commonly observed is availability of time data. So you have timestamps associated with data, which means when you are structuring your problem, it's not going to be just random pieces here and there. You actually have an order existing within the data set, and that helps you define a problem. That you can build a problem where it's a time series problem because the data available to you already is on a time series. Similarly, there are data sets around in health. You will have data sets around particular IDs. So these are anonymous IDs, but all the records are associated with that particular ID. The benefit of that is you have a lot of information centered around one particular entity or an identity in maybe multiple data sets. One can be around medical imaging, another can be around health statistics obtained over time. There are data sets about the gene sequences. So different kinds of data sets might have a scope of collaboration, which are like listed in health particularly. In terms of economic empowerment, the data sets that are available for public and social sector, economists actually, the PhD people who go into policy making, right? Their main sources are those data sets. They are looking at census data. They are looking at several large data sets of surveys around public sector domain, usage of different utilities, and they map all that in terms of defining the next steps that they take in policy making. More around infrastructure and economic empowerment is that people have data sets on the geospace, which means you have a map of a city and you divide that map into different blocks, and then over each block you have a certain you have actually a large number of features. So what are the number of what is the population density of a particular block in a city, right? Now you have that. What is the percentage of hospitals that are provided there? What are the education facilities, and so on and so forth? What are the distance to markets, recreation activities? So when people are doing city planning, they have access to all this data, right? So they have started to use machine learning in a way that how can we improve certain other areas of certain other areas and neighborhoods, looking at the successful factors of the existing good areas. So there's a lot of mapping that happens between these, but broadly, if we have these 10 domains, we end up thinking more in terms of a particular problem being solved by the availability of a data set, most of which are already available or at least are easier to obtain. If we center ourselves around environment, right? A lot of data is available from remote sensing. Then there are data sets so if you're looking at impact of pollution over a region, you have certain remote sensing data sets which are around the plantation, whereas you have data sets from the transport department around the number of vehicles that are running, what are the emission rates, different things. So this is just constructing a large amount of information in order to derive features that might lead up to a certain conclusion. When I go over the process of machine learning pipeline today, you'll understand more around the features and why I'm talking so much about these obtaining different features. But the idea is if you want to learn any kind of property, you want some input going in. You want to put, when you're learning from the data, you want to extract any identifiable information from the data, right? You want to use whatever you can to build on to the next step.
But ideally, is there some way to like map, to have like translations between data sets so that we can develop solutions that work between the different domains? Or do you feel like it's kind of, they're like siloed based on the different like components of the data set?
So broadly, they are siloed because they are controlled by different departments. But if one organization has control over different data sets, and then they have the correct rights to do the mapping, let's say. Then we can use different, when these government departments come into the play, right? They have access to several data sets, and if a mapping can be formed between those data sets, then in most cases, I think they have the legal right to do that. So then this mapping is possible, and two different data sets can be used. But if I'm someone who is collecting a particular kind of data for just a specific case, I may not have that access. But looking at a normal user, what you can do is you can use the identifier portion to map the data sets. The common key between two different data sets can be something which is in the public domain. So one example, which doesn't have much to do with social good, but in terms of understanding how to map data sets, is if you're looking at stock prices. If you want to do stock prediction, right? You have a ticker symbol, which is the key that you want to deal with. That's your identifier. And now one data set can be extracted from the stock data repository. So there are different APIs you can use to access, let's say, like 3 years of data on the stock AAPL, like for Apple stock. That's my one set of data. I got all the numerical figures of market close and open for past 2 years, right? Now I want to do the prediction with more data, because, okay, even if I have numbers, I can build the regressions, but there are several factors which are actually affecting what's happening on an everyday basis. Can I do something to learn that? Maybe there was news associated with this stock, with the ticker, on a daily basis, which is the case. Like all these, if you read Wall Street Journal, whenever they mention the article, they also mention the ticker. So if you are writing a web scraping tool to extract information from, let's say, Wall Street Journal, you can use that keyword to find the information on an article. So if you have access to, let's say, 2 years of data of Wall Street Journal, 2 years of Twitter dump, right? You can extract all those information with that particular identifier. And now the data going into the model for learning stock, for predicting the stock of Apple is not just the stock values, not just the market values. It's that data along with maybe, let's say, tweets around that particular ticker symbol over the past 2 years. Then you have news articles. If you have access to more data sets, which are, so there are forums where people are communicating over these things. If you have access to that data and it's in the public domain, if you have Reddit data, a lot of data sets can be mapped. So the identifier has to be something which will allow you to do so, right? So that's why, I mean, even though if the data sets exist in silos, if you want to extract information from a different data set, some kind of relation can be created. Okay, so that's the first thing. And then what this paper does is it these are examples. Then this paper maps them to the United Nations global goals. So there were 17 goals that I discussed. I did not discuss them in detail, but the 17 global goals that I mentioned in the previous lecture. Why we put them as sort of a benchmark is because real experts in the domains have actually worked on those, and us being computer scientists entering into that domain, I mean, we are not the ones in the position to really define what are the good social goals. So if we can use some predefined state and then map our understanding to those things, it's best. So they map these AI use cases. The important thing to notice is that UN goals are not one-on-one mapping with the use cases. Multiple use cases can actually help solve, or at least help make a difference in one or many of the goals. Health being the one where we have most of the success so far, and I expect that to be the case. Health anyway is like one of the most important social problems that we want to look after. Poverty, hunger, I mean, they all change with change in health. So health and education, when we are looking in the social domain, are extremely important anyway. With more education, the impact on other domains is clearly evident. Same goes with health. So this mapping is, any questions about this or any comments on this? Like, why would we do this? And if we are doing this, what are the advantages beyond what I discussed?
You need advantages in terms of quality.
those include other tools, or? Well, I guess there are specific use cases that you can go ahead and approach specific problems that you might not have thought of. I had considered, life below water, because water access is something that AI can help solve. But apparently, was a use case, which I was surprised, but pleasantly surprised.
Absolutely. Yeah, so there are these tools which, like below water is the same case for me. I mean, I hadn't thought about it properly. So there are these domains which just can be taken care of by AI in so many cases. And actually, like below water is a lot more practical because imaging data underwater, it's possible to gather that. And you don't even need humans to actually go in and collect that, right? So imaging data can be collected by submarines, and it can be set up to just keep on building a large data set over time. You set up cameras on a submarine, and then you are deriving a lot of data over time. And then, I mean, since problems haven't really been addressed in these domains much, any improvement would help. Any improvement would start to help or start to give a direction. So another great thing while trying to apply machine learning for social good is that the process with which machine learning operates, you, even before building an ML model, you're looking so much at the data that you might end up with some analysis of the data set which helps the society, right? You may not even have to build a prediction model which will give you a great result. Already looking at the data, you draw some correlations which are just leading on to some assistance. I mean, if you tell those correlations to the people who are working in those domains, they might actually see some significance in it. So the process in itself leads on to greater results. And the third mapping that they did is AI capabilities that are known capabilities at this point, which are going to expand over the years. But right now, based on the state that we know, how do they map to the 10 goals? I don't know if it was fit on the screen.
Instead of putting the whole thing on there.
Yeah, then actually it was on the previous slide. Should I zoom on like smaller parts?
Yeah, just.
Okay, yeah, okay. So, okay, let's see. Deep learning on structured data. So that's the first one which I mentioned in terms of the data sets that are accessible as well. That you have your data laid out so well already in columnar form. People have tried to, so there's a process of feature extraction. I will go over it in detail, but if you have general idea of machine learning, you know that whenever we look at data set and a model, we try to extract features from the data set, right? Those features at the very basic level, without really much processing, can be just characteristics of the data. So if you have data, census data, and you have household as the key, there are different pieces of information, different columns in that data set that you can build, right? You can build average income, average number of, like average hours of work, what are the, like food consumption, and different statistics depending on that particular entity, right? So most of the data sets in these domains already have structured data somewhere predefined. Very, very basic learning models. You can have sort of linear regression models, which fall under sort of the most basic category, can use information existing in these structured data sets, deriving certain kind of prediction, which is better than just a coin toss. So, and if you have anything better than, so if you take any data and it can lead on to, let's say, 10 different things, right? 10% is your base probability. 10%, I mean, if you do anything, 10% of the times you're correct by just saying one of the classes, right? That's the general distribution over a particular classification. Over a binary classification where you can say yes or no, like you have two predictions, your coin toss is 50%, right? So if your learning model with simple information can do better than that, then you have at least solved a part of the problem. You have given them a direction in which they're not just doing guesswork. They're doing slightly informed guesswork. Maybe not well informed, but slightly informed, right? That's one step up. Then you build complex models. If you have enough data, you can build complex models. If your data conforms with the architecture of your learning model, you can build much well-defined models, leading up to things like image classification. The current state of the art is great, right? You can, and the classification on MNIST, there is a famous data set of digits, of images of digits. The classification accuracy is beyond 99 point something percent, like 99.4. That doesn't generalize well to everything else in the world, but on that particular data set, if you give a neural network an image of a digit in black and white, in grayscale, it will identify the correct digit. That in itself is a great thing, because now you have all this handwritten documents all around the world. Even if you're not able to translate the text portion of it yet, the information that is around the digits, the numerical information, digitalizing it is going to be easy, because you have this model which has such a high accuracy that it will just basically give you the right numbers all the time. So this is sort of the extreme side, that when you have a training model which works so well. But from just going beyond the random probability to going 100%, you have all this pathway, and that's where you want to put in machine learning. So deep learning unstructured data, if there is access to any kind of data set, just building up small correlations to some linear models, everything helps. And for these sectors all around the world, this help can mean something really big. I mean, in terms of data, you're saying maybe I work on like 1 million data points, but if those 1 million data points are actually affecting even 1,000 lives, that matters, right? So the impact of machine learning in social domain can just be a big impact on society in general. Natural language processing. Why is it so important? Because that's the way people communicate, right? That's the way people, even if someone is expressing a problem, it's going to be in a certain language. So if you have any progress around natural language, either understanding, either generation, or parsing, translation, the entire space of natural language processing is going to result into big impact in everything. So info verification and validation is a big block in natural language processing. That's particularly because it deals all around information which is text, and you want to do verification and validation. If you have well-trained natural language processing models, they will be able to understand what the content is and then do the verification that's required. At least you can do fact checking, you can do certain kind of mapping, whichever is possible. But having access to learning models, even if those models cannot do ultimate level of fact checking, they can boil down to a smaller set that a human has to deal with. So if a human was responsible for fact checking each and every document, whereas some of those documents did not contain any relevant information at all, even a poorly trained ML model would be able to eliminate those sets, reducing the load on the manual worker. And with improvements, this just keeps improving. Another is object detection and localization. The current use case, what's the main current use case of object detection and localization right now? What's the most popular use case? Mm-hmm. Autonomous driving, exactly. That's one use case where if you don't do any detection, then that's step one for autonomous driving, right? You want to detect an object. Even if you don't classify an object, you want to detect it. Even if the car doesn't know whether it's a pole or a human, it has to stop. It doesn't have to hit into it, right? So detection is step one for an autonomous vehicle. But detection in itself is the ability to give a learning model a certain sense of where in a broader picture is the object of concern. When you set up cameras to do, let's say, surveillance, right? The image, for a human in an image, identifying different important entities is just I don't know. That's how we operate, and there's no real definition of saying, "Oh, this is how I'm able to differentiate a certain person from the background." But for a camera, that's not the usual case. So, object detection and localization models, they allow this. They are able to train the camera, train your system behind the camera in such a way that at least looking at an image, you can boil down to the coordinates of the object under concern. How well are you classifying over there? How well are you sort of doing the process beyond that step? Can improve over time, is improving over time. The state of the art in object detection is improving very quickly. But the first step of detecting, again, is a big help, right? So now if I have a surveillance feed for 2 hours and there was someone who was in charge of taking care of it, right, looking at it, they may not have to look at entire 2 hours because the learning model is able to eliminate the ones where there was no object of concern. Because the model is trained well enough. You have surveillance of a farm, right? Your farm remains in a certain state, and you want to detect if there is someone coming in, right? The difference between that image and the image where someone is coming in is going to be easily, and that is easy to train. So now you don't have to look at 3 hours in which there were 5 minutes. You probably have to look at the 5 minutes and a few minutes here and there to derive more information. But it reduces the workload on someone who was going to do a lot of manual work. So object detection has been used in equality and inclusion. In infrastructure, infrastructure is where you have cities and traffic. In that domain, particularly, object detection is sort of a major use case. Language translation, I mean, this is known, well-known. Language translation has, there used to be a domain called statistical language translation, SLT, statistical machine translation, I think, SMT. And now it's for more of neural machine translation, the new domain, which is based solely on neural networks. And neural networks are currently state of the art in machine translation. And there are challenges every year. I don't remember what are the latest numbers, but they are getting closer and closer to human level performance, which is great. You want to be able to translate texts between different, translate from one language to the other, provide access to more and more information which is publicly available, but is not accessible to someone else, right? If we can make that make that transfer possible, it's going to start making a bigger impact. A big problem in developing countries is lack of access to knowledge is restricted. Access to a lot of research that has been conducted that can be used to improve the state. There are limitations. In cities in most of the countries, things are different now. English is widely used everywhere, but once you start going into the remote locations, it changes. It changes drastically in almost every country. So how do you provide more and more local language access of content to people, even if it is not perfect? People can make structure out of slightly broken language, but still this allows you to make that transfer possible. Content generation. Content generation is something where, in terms of research, steps have been established, a lot is being done. One of the biggest use cases of content generation is Alexa, or the voice assistant, not just Alexa, Google Mini, Google Home, and Siri. So the idea is that you're not only making the machine understand natural language, you're also making it generate natural language. The domain is also called natural language generation, NLG, where based on the existing samples of text and speech, the machine learns how to really build on, how to create a new piece of text. You might have seen content generation methods are also used around imaging. So does anyone know what are GANs, generative adversarial networks? So I had not. You can explain.
So my understanding is that you have one network that's generating content. The other network's trying to detect if the content was either generated by the first network or if it was something that was genuinely made that the network is trying to attempt to simulate.
Right. So briefly, what a GAN is that it's training two models together. One model is responsible of learning, right? So you have data, you have an outcome. One model is trying to do the learning. The second model is trying to do generation. It's trying to generate the representation backwards. So there's a generator and there's a descriptor. I think it's a descriptor, but discriminator. So the idea is that you want to learn, keep learning the outcome while also reaching into a function which is describing how the content was generated. At the end of this, a GAN basically obtains a good understanding of how to generate content, and it's being used to generate images. It's being used to generate speech, and I mean, it's in the experimental stage right now, but it's a promising piece of technology. So after this class, maybe you can take a look at GANs as well. So that's the general idea of this paper. Any particular thoughts? We'll have a discussion on Piazza as well, where if you haven't read through the paper properly, you can go over it more and start discussing points. But there is a great component of reading, which is combined Piazza and the discussion over here. So, I mean, plus readings are an important part to understand this domain anyway. There isn't much out there right now, but whatever is there, I have seen like really important people being involved in it. There's another paper by Professor John Steinberg. It's an article, not a paper, but based on a paper that they did for policy, for use of AI in policymaking. That will be in the part of the next readings. But in the recent, like from I think 2016 onwards, I've seen really big people being involved in this domain. So there is future. There is hope that this picks up, and AI for social good workshop is already taking already a big thing now. It's going to take place in iClear in May. If any, ICLR, there's a conference called ICLR, International Conference for Learning Representations. One of the main deep learning conferences. I think it's going to be in Vancouver. No, it was in Vancouver. So this time it's in New Orleans. So they have a workshop on AI for social good. If anyone is attending, that might be a good venue. Okay, so you want to continue the readings, or should I go over the machine learning part now? Break? Okay, let's have a quick break, and then I'll go over the introduction to machine learning pipeline. So moving on to the machine learning side, why do we need machine learning? I've just mentioned like a few small points. There are many reasons around it, but the idea is that there are many problems that can be just fixed by a formula. You can write some deterministic solution, and the answer that comes at each and every step is correct, and you use it, right? Doing normal calculations. You don't need machine learning to do your normal calculations. They are done in a certain way, the answer will always be the same. But there are several problems where you can only approximate the situation because you have an understanding, but you never have a clear formula. So you look at the data, you look at what has happened over a long period of time, you look at the data set, and then you try to create a function. You don't have a defined function. So you need a tool. Machine learning is one of those, like one of the tools that have really been highly useful in that context, right? Now, another thing is when things change over time. So you have a situation where the data evolves over time, right? So it maybe for the current time, there was a formula that used to work really well, but then things change, different factors get involved into it, and you want to learn something new. So need of machine learning is sort of well understood, and also there's a limitation to what humans can humans can infer out of a situation, right? Humans can look at things. There are several things which are really easy for humans to do, which you cannot teach machine. But there are many things around large data assets, looking at a large amount of data and drawing conclusive information out of it. That is not something humans are great at, whereas machines can be taught to do that pretty well. So what is it that we are doing when we are saying machine learning? We are assuming that the data that we had access to, the data, underlying data, came from a certain distribution. It had a certain representation of the truth, which we could not understand, but there was something underlying. There was a distribution underlying it, which was a visual of the reality. And now we are trying to build a model which is as close to that reality as possible, right? That's our objective. The very simple approach would be, we have a mathematical formula, right? And that's a fixed formula. Now we take a lot of inputs and outputs. We put in, so a simple equation, ax squared plus bx plus c, the quadratic equation, right? You take a lot of data and you pass it through that equation. You don't know the values of a, b, c starting, you define certain values of a, b, c, but the machine learning model doesn't know it, right? What you do is you generate a lot of data by that formula, and now you train the model. If the model is able to come back to the original values of ABC, you basically have mapped to the distribution that was your original distribution, and now you have minimalized the loss, right? So that's the approach that we are taking in machine learning. We are trying to reduce the distance of our hypothesis from the original distribution. What are the commonly known types? This list can expand, but it can also be just summarized into these four. One being supervised learning. You have some inputs, some data. They correspond to certain ground truth, right? If you have X and you have basically Y associated with it, can you use that information to build a model which, when given new X, would generate a new Y which is close enough to the true Y? Vaguely abstract, but what I'm trying to say is that you have some truth associated with the information going in, and you're trying that to learn a model, learn a machine learning model that, when given an input, gives a certain output. You predict that output, take that information back, and update the model. I'll go over that later in the process, but that's the idea of supervised model, that you have certain ground truth associated. Unsupervised learning, whereas, doesn't have that particular ground truth associated. But just by looking at the data, there's so much that you can still learn. So in the current term of deep learning being already so famous, word embeddings fall under that category, where you look at a large corpus of data set, you look at a lot of text. So you have large amount of documents. Each document is written in, let's say, just English documents, right? So they have a certain fixed vocabulary of words. And now, by the co-occurrence of different words together, so in a sentence, right, types of ML. So in this sentence, I can say that of and types are neighbors, because of comes after types, right? So this kind of relation that is not leading to any major conclusion, but is something you can observe in the data still, can be used to learn a representation, a vector representation of each and every word. That's a domain called word embeddings. I think we are supposed to go over that stuff next week, but that's a big application of unsupervised learning being used almost everywhere now. So there's a, I mean, maybe you have heard the name in any case, like word2vec. Do you know that algorithm? Word2vec. It's a famous algorithm. Word2vec, VEC, vector.
I thought that was trained in a supervised method.
That's unsupervised learning. The way they are doing it is they are converting that problem into a supervised learning. It's called NCE, like noise contrastive estimation or something. But they, I'll go with that later. But it's a space of unsupervised. You don't have any fixed. All you have is your corpus, where you have words in sentences. You're constructing a problem out of it, which means that given these two words, whether they have a context pair or not. Let's go over the details later. Corpus is just a large data set of text. Semi-supervised learning, which is similar to supervised learning, but now you don't have your output, the truth for each and every data that goes in. For some samples you have, you use that as a starter piece of information, and then you build on the model on top of it. So in the first lecture, if you remember, we were discussing one of my works on fake news detection. The fact behind that was that we don't know too many sites that generate fake news, and we cannot flag sites as being like fake news websites just on a hunch. We can only have a very small number which has been definitely identified as a source, and then that's the only ground truth we have. For everything else, we are just going to learn whatever we can. So semi-supervised learning process follows. So the process that we follow in that particular paper is semi-supervised learning, where you have some known truth. You're using it to sort of start off better than just starting off at random, and then build on in an unsupervised way. So these are interactions within the data itself. So the way to solve different problems in unsupervised learning or semi-supervised learning is to convert them to supervised learning problems. But the final objective, the final thing that you want to obtain, does not really have so much truth available. You are constructing a problem from within the data. How we do it, it would, I mean, those will be covered later, but let's go over it quickly. Reinforcement learning, that's another domain. I don't think we'll be covering it during the course, but this is a method of learning where you have something evolving, something is learning, and you're giving it a feedback. You're not giving it the value that this is the answer, for this input, that's the answer. You're sort of giving it a step-by-step feedback that, have I reached the answer yet? No. Have I reached the answer yet? No. And the point when you have reached the answer, yes. So that's sort of a way to.
Supervised, like you said.
Mm-hmm.
That sounds supervised the way you said it.
No, that's reinforcement, where
Well,
you're sort of giving it
Because
the
usually you don't know whether the answer is no or yes. Often you just have, you know, like, what is this, a good or a better, you know, step? Well, I think of all the video game examples, right? Usually
Yeah.
they're just based on like a score or maybe some notion of progress.
Yeah, so there's a final outcome that you want to reach, the final state where you say the game is over or the game is complete, like you have reached to whatever it is. So the feedback going in at every step contains this piece of information that, have I reached that step? Have I reached the final outcome? What is my current state right now? So it proceeds in that way, that you're providing it a minor feedback. You're not providing, you don't have access to the full mapping of this input leads on to a certain output as you have in supervised learning. So reinforcement learning goes in sort of a like feedback at every step, state transitions. Some of the common learning problems that are, I mean, these are most commonly discussed. One is classification. Classification can be of different types. Binary classification means you have two classes and you're just classifying your data to be within those two classes. Given a problem and given a particular question, is it yes or no? Sort of that kind of situation. Whereas multi-class classification is when you have your answer across more than just two options. So in binary, you have two classes, which is yes and no or right and wrong and whatever is the situation. But in multi-class, you have multiple classes. And in multi-label, you have different classes across which you have the outcomes. So multi-class follows the way that if you have an image of a flower and there are 5 kinds of flowers, which class does the flower belong to, right? Whereas multi-label would be if you have an image of a flower and the classes say it can be a flower and the particular kind, and those are 2 labels, you want an answer of yes sort of on both of these. Not a great example, but one input can have more than one correct answer in multi-label, because you have same thing can mean a lot more. Like it has multiple labels associated with it. Whereas in multi-class, you're saying which class does it belong to. You're still putting it as a full-on classification problem between different classes. Multi-label has like in object detect in in object detection, the final process can be generally treated as multi-label because there's a class, let's say, called automobile, and then there's a class called car. If you find a car, you want it to be yes on both, right? But car is sort of a finer thing that you're doing. So you have classes called automobile, truck, car, bus, right? For each of these truck, car, bus, you also want to predict automobile, but you're predicting one of the particular ones. So that's more centered.
So could it be that, like, I have one, like in this room, I was detecting the objects, like one would be, know that it's a chair and also know it's a chair with arms versus a chair without arms. And then another one is know that it's, like a wall hanging and that it's also a chalkboard versus it's a wall hanging. I don't know what that is. Hopefully that's not art. You know what I mean? Like, is that what you're saying? Like, to give it all different kinds of things, and then you get to know what kind of thing it is, and then what specific kind of thing it is?
That was the example I was going at, where I had to know what kind of thing it is and what kind of specific. But in multi-label, you don't have to have it as a subset. But one thing can have different properties, different labels associated to it. So you want to sort of learn the probability of, there's this challenge on, I think, Kaggle again, which had a piece of text, right? And then they had 6 hit categories, and they wanted to identify whether it belongs to any of those categories. So now it's not a unique solution problem. You basically want to associate certain probability to each of these categories. Probability being 0 means, okay, not at all, but probability being significantly high in 2 of these is possible. Whereas in multi-class, what I'm saying is that you have a situation where you have buckets and you have to put your object in one of those buckets only, right? Whereas in multi-label, you have like tags or labels that you're putting on your object. Yeah. Then regression is another family of problems where you're not sort of doing this bucketing that I talked about, right? You're not putting things into particular zones. You're predicting a numerical value. You're predicting a floating point number. Stock prediction. That's generally a regression problem where you have a certain number going in and you want to predict the new number. Probability prediction, it's a mix of the two. What you're doing is you are predicting a number, but it has to be within 0 to 1 because your number is definitive of the probability of something. So if you are predicting the probability of an object being of a certain color, let's say, the value that your model should emit out should be a floating point number between 0 to 1. That's the probability that it's learning. So it may not need, it's not required to be a specific category, but looking at it in this way often helps. I mean, it helps figure out that when we talk about classification, binary classification, it may sound a lot like probability, but sometimes all you need is probability. You don't need to do that final bucketing.
That distinction, you got the ground truth, or I mean, because all these models generally have the probabilities.
Mm-hmm.
So the probability prediction is that more about the ground truth not being ones and zeros, but also having a probability.
Yeah, where it boils down to a regression problem.
It seems kind of like regression.
Yeah, that's what I'm saying. Probability can actually be a mid case of binary classification where you're not doing the final bucketing step, or it can be just treated as regression. But regression as a general problem is not limited to your 0-1 block. Probability is, right? In regression, I'm not limited to predicting something between 0 and 1.
If you have a set of images and you're trying to classify if they're cats or dogs, and you put in one image and you get like it's 98, the system is 98% confident that it's a cat.
Mm-hmm.
Is that probability prediction?
That
Or is that
if you treat your answer as the 98%, right?
Yeah.
Then you're predicting a probability. If you treat your answer as cat was 98%, right?
Yeah.
Yeah, then it's binary classification. It's sort of which step are you stopping at?
Okay.
That's why whenever you will look at text, it would say two kinds of machine learning problems, classification and regression. But probability is that one step which is a better tool to communicate many times. If you have a detector, right, then you don't care about the probability score. What you want to emit out as a final value. Most of the times you want to classify. But if you want to stop at the probability value and use that, probability prediction can be created as sort of a category. It's a mix, so it falls under both of these. Okay. So now this is sort of a pipeline of how you start with a machine learning problem and you evaluate it. So we are not talking about the deployment phase that I dealt with earlier, but in the process breakdown of identification, definition, solution, and deployment. In the solution phase, once you have defined your problem, how do you actually build a machine learning pipeline? So the first thing is gathering the data. So you have a problem, that's where you started. You did not really know much, and you just try to find out different data sets, right? So in gathering data, you want to find the right sources of data. Depending on your problem, you might already have a data set access. You may have to run some process to create data out of different data sets that you have. But the first task is to find those particular elements that you will you will build a learning model with. So finding out where you can get the data, finding it out, setting up identifiers responds to the fact that I was talking earlier. If you have different data sets, right, like the stock data set dealt with, the identifier was the stock over there. So an identifier is required to map different data sets so that you can sort of accumulate all this information available from different sources and make it a part of one row in a table if you start the row with your identifier. So finding the correct identifiers. Then there's the mapping the data to requirements, which is again, you have a definition of a problem, you found out a certain data set. Is this data actually making sense with respect to the problem? I mean, you have a problem in traffic department and your data set talks about just other demographics or like just doesn't talk about the particular state. That might not be the correct optimization. So does it contain the right set of information that will help solve your problem? It's similar to finding the right source of data, but once you have found maybe let's say multiple sources, boiling down to the correct data for your requirement. It's sort of a manual process where you're looking at data, defining correlation, sort of trying to understand whether it would make sense, whether it would help you solve a certain problem. And then you move on to cleaning up that data. Cleaning up is an important part because when you acquire data from a real world situation and not from a pre-cooked data set, it's hardly clean. I mean, and there are going to be entries with almost no inputs in most of the fields. There are going to be fields with just default values built in. So several times what happens is that if you take a data dump from someone and they did not structure the defaults to mean to lead on to, let's say, like an empty or a zero value, they can have any kind of default. And now if you don't clean that up, your model is going to learn a lot of that occurrence, and that's not some piece of information which you want your model to learn. You want to eliminate that information, or you want to at least make some measures to control this process. That the model should not learn just vague values. How do you clean that up? And there's a full space of work on cleaning up data. I think there's one more course over here as well, which is dealing with it, 184. 184. Yeah, so I mean, cleaning up data is a big task. So in most of the cases, try to find a source which is clean. That's an easier process than going on cleaning data. But
I'm curious what they teach in the data course I'm
just know there. So I mean, cleaning data is not the only part of it. It's data wrangling, extraction. It's a lot of stuff, but they have they focus on cleaning data part of it more. whereas I just put it as a bullet.
Cleaning data just always feels like such a, like, you know what to do. It's just routine, like a lot of coding work and like just,
Many times it's even beyond that. I mean, in some cases, I had to build sort of a dictionary specific spelling correction model. So usually for spelling correction, what would you do? You will map it with some source, right? You have a dictionary and you want to do a spell check. But if your data has a lot of spelling mistakes and you still want to learn, I mean, not mistakes, credit card, right? Let's say you have a data set where someone wants to write the word credit card. And now sometimes they write CRDT, CRD, or like they're doing different short forms. And you want to boil all those words into one. And there's no fixed list that you had access to. You just want to learn it in the process. So that's a data cleaning process because you don't want to feed this information as different words to the model. You want to learn in some way that these are common words. And that's not a fixed piece of code, that's an algorithm
yeah,
process.
I'd say that back 100%. It's up, it's not always clear at all what to do. I'm just trying to imagine like the curriculum for a course like that. It would be cool if someone really experienced that.
Yeah. So, I mean, there is a class where it talks about entire process with data. So that might be interesting. Okay. Once you have the data set for a proper process of learning, this is the split that we do. We want to train a model. So before I actually go into the terminology, everyone is comfortable with the word train, right? Is there any question about why I'm using this particular term, training a model, validating a model itself, right? Because I'm taking those to be, I'm taking them as granted and moving from that. Okay, so the training set is the data on which you will optimize your model. So you start with a certain hypothesis and then you keep training it and you want to sort of reach up to the parameters that are the best representation of the reality. What data are you going to use for that? That's your biggest set of data. So you build a training set. But while doing that, do you even know that it was a good generalization or were you overfitting? So overfitting sort of means that you just memorized all the data that was given to the model. And if anything comes in from that data, your answer is going to be right. But you don't really have a general picture of how things work. So high accuracy on training data alone is not really a great measure of a good model. So for that particular case, you have a validation set, which means that in the process of training, you are performing a training round, you are training your model, you are making it generate certain results, and then you are evaluating those on a small set, which was not a part of the training. So some data, which is different, so these are all parts of your full data set. So you have a large data set, and then you want to randomly distribute it into 3 partitions. In those partitions, what you are saying is that given the model trained on a certain training data set, if it gives good results on my validation data as well, then there is hope that this model is learning something. But if it's giving great results on training, but very bad results on validation data set, then you haven't really formed a generalized model. You have probably created a model which is learning something which works in the case of your training data. But if you give new data to it, it won't generate a good result. So validation data set is usually very small, and you use it while training the model so that you can keep on updating the model. And once you have a reasonably well-trained model and you have established, okay, this model works well, it shows good results on my validation data, let's put it on the test with another data set. So which is slightly larger than validation data, usually smaller than training data set. There's no fixed rule that it has to be. A larger test data set is actually a good evaluation measure itself, but in most of the cases, because we don't have infinite amount of data, we want to use as much as we can for training the model well, and then we evaluate the final results on test set. If your model shows great results on test set, that is a better, that is sort of the certificate that you give to your model. You're saying, okay, if the results on my test set are great, then it's a good model. That would be the benchmark against which you will evaluate all your models. That no matter what was the accuracy on training set, even if in training set one model was doing better than the other, if it doesn't do better on the test set, then you cannot assume that it's a better model, because again, better results on training set alone are not a good indicator. So this part is clear, like training, validate, test. Okay. So now second step in the process is you have your data, you have made the partitions, right? Now you want to extract features out of your data. You want to convert this data into something which a machine learning model can use, right? You want to pull out information from it, structure it in a way that can be fed into a learning model, and then you can continue with the learning process. So extracting features is a big thing where you want the right set of properties from the data, right? The data might contain a lot of information. Maybe all of it is relevant, maybe some of it is relevant. You want to find out what it is that you can. You want to see what are the features that will help your model, right? And third is building derived features by using certain properties. So several times what happens is that the way your data appears, it just has, let's say, one column defining something, but that column itself can be used to build more features. I'll give an example later, but deriving more features from an existing feature, just to increase the number of, increasing the amount of information that you are going to feed to your model. Then you have like setting up methods to learn features, which takes us to slightly the side of neural networks. So one thing that neural networks do really well is learn the features themselves. This process of feature extraction is a lot more important in smaller models, whereas in neural networks, you want to feed it the data directly and try that the model learns the features. They may not be features that you can express clear definition to. You cannot describe them very clearly, but they are good features for learning the real model. So neural net does a great job at learning that. And the final point that I raise over here is obtaining transfer features from pre-trained models. This also leads on to the neural net thing, which means that maybe for your particular data set, you can only extract a certain number of features, right? You have a text data set, and you have, let's say, communications between different users, and you want to draw some inference out of it, but the data set is not that big. So while you can still build some learning model out of it, you may not be able to build a language model or build a model which helps you define the meaning of each and every word. So in cases like that, you can use some pre-trained models. So there's something called GloVe, which is, I don't remember the full form. It's a big word embedding data set from Stanford, most likely from Stanford, which has a large number of words and vectors which are learned already from a big data set. So if you just use that data set going into your model with each and every word, so at every word from your text, you want to learn something, but you only have so much information. But if you associate this vector that GloVe has already provided you, you're adding a lot more information which could not be derived just from your data set. So that's the process is called transfer learning. It's heavily used in neural networks, particularly in text, where things like embed. So GloVe is one example of embeddings. Second, it's also used in images. So most of these object detection models, they often use some pre-trained image classification layers when you're training an object detection model, but you're not starting with all random parameters. You're starting with a pre-trained image classification model and building using it as a part of your bigger model. So these are things which help you extract some features which are learned features, not self-derived, self-cooked features. These are actually learned by the model itself. The pre-processing part and features is that when you have the manually extracted features, and even in case of neural nets, you cannot just, I mean, you do need to pre-process your data so that it can be fed to the learning model. A language text data set. If you are feeding it to a neural network, you cannot just put in the sentences as it is. I mean, you have to do certain mapping to some structure which the model will understand. The model ultimately is going to learn weights on top of numerical values, right? You have to reach to that mapping. So there's this whole set of pre-processing, whole step of pre-processing that has to be performed while going into the learning process. So features can be of different types: text, image, date, time, normal numerical values, right? And image data looks completely different. So the original way of doing computer vision research was that you would extract a lot of information out of an image, because there are so many expert level methods to do that. And then you pass that information to a learning model. Whereas the convolution, the new method that convolution neural networks use is that you are sort of putting in just the direct pixel level information of an image. So an image can be seen as an RGB pixel map. So if it's a fixed size, at each and every pixel you have a certain value of red, certain value of green, certain value of blue. That's the information that you're sending to your model. So different models can take it differently, and there's a pre-processing that you have to perform, which is an important part. So how I'll be covering different machine learning processes, that I'll go over some of the components, right, broadly. I will do a little bit of coding, and the assignment will help you do that. But if you have good background, these should be straightforward. If you don't have much background, I'll add resources in the lecture notes so that you can look at good tutorials and resources that can help you build this skill faster. But all of the machine learning process I'll be covering in like very small amount of duration, because there's so much that we want to cover in the course. So there's a link to a crash course in machine learning by Google. It's sort of teaching through TensorFlow, and they are, I think, teaching a lot over the concepts as well. I was looking at it, and it had some major descriptions of how much time to be expected. It says 15 hours. So total of 15 hours is not that much time, and maybe you don't need to do it till the end as well to really have a good idea of how to work with things. But I'll add a link to that particular course. It's good to get started in machine learning, start using different tools. Also, the technical setup that you would need on your machine. I'll put a post specifying some of the main things to do so that you can set up a Python environment on your personal machines, and how you can just start building small use cases.
So related to that, there are 4 GPUs on Hummingbird.
Yeah.
They're supposed to be accessible to you.
Yeah, but then one user logs it at once.
No, they're totally unused because students don't actually have access.
I have access. I have used those.
Oh, you've used them?
Yes.
Because I spent a couple months with ITS. Back and forth.
So if you have SOE access, you can use Hummingbird, and you have to launch the process using Slurm.
Yeah.
So then you can use, but it's just one. So if you're using that at a certain point in time, that's logged, but hopefully your process won't take that long. But there's one, and I think it has a P100, but there is one node with 4 GPUs.
Yeah, 4 people. So you've actually gotten those to work.
Yes.
You have to show me how this happens.
At some point. I have the scripts and everything. I'll show you, but that's still not good enough resource. There's citrusdance.soe.ucsc.edu. That server has a GPU which has 5 GB or 6 GB memory. So
really,
technically you can, you have access to that, but if you are running any reasonable size of learning model, it's not going to be.
Oh, really? My experience is everything takes a GPU. I mean,
so CitrusDance GPU is really small. I mean, if you have a convolution net with even 3 layers, it might not work. So, but that's a later topic. We'll discuss it outside the class. So for the pre-processing part, like I was saying, the model should be able to understand how to deal with the data, right? So let's say we have a text which says a quick brown fox jumps over the lazy dog. How do you explain to the model what it means? Can you do some kind of different representation in which you're sending this information, right? So two of the examples, I mean, there are different ways, but two examples are that you just specify it as a sequence of different words. So what you're doing is you're creating a dictionary where each and every word in your data set is going to be a part of the vocabulary, right? It's the dictionary is your vocabulary. And now for each sentence, you just say this. Like you're just representing them with an integer symbol. What the way it helps you is that now the model is looking at something it understands more, numbers, instead of looking at text, right? Raw text is not easily understandable to a machine learning model, whereas when you start putting in information as numbers, there are well-developed ways. There is something called embeddings. There is something called one-hot vectors. We'll cover those probably later on, but there are different ways in which the model can now understand. So that's one of the ways. The second is that you say, okay, this is a fixed set of words that I use all the time. And given a sentence, I will just say what is the frequency of that word. So in our case, we did not have, I mean, I just put it over this particular sentence. So we have all the words. But now this count vectorizer is not indexed by the sequence. It's not holding the sequential information of my sentence. It's holding the word occurrence information. So I can move the two somewhere else if the index of the changes, and then I can still use that count vectorizer because I'm just saying this particular word occurred 2 times. That's the information I'm giving to the model. I'm not saying that quick occurred after the, that order information is not existent in this case. So that's an incomplete way of representation, but sometimes for a smaller model, an incomplete way might be helpful. So use count vectorizer. There are different kind of vectorizers. I'll have links to the documentation to go over these. But this is just an example of how you start to convert your text data into data that can be understood by the learning model. Similarly, date time. So date time is something like this, Monday, April 8, 2019, right? You have your time, you have your time zone. Looking at it, it's just timestamp, but there's so much information that can be derived out of it. So this is also corresponding to the fact that we can generate derived features, which is looking at a particular piece of information, you can derive year, month, day, week, day of week. Day of week is a very good example of a feature that, I mean, I've used it personally in several applications, and it helps because when you're looking at certain actions of data, day of week matters. The difference between weekend and weekdays is important. Similarly, time of day. If you are building a model of, let's say, predicting some action, predicting whether your post will be delivered at this time, right? That particular time block has information. So at which time during the day is it happening? That's a relevant piece of information. So from your big feature of date time, you can derive a lot of useful features. Numerical features. Generally, they are good to use directly, but they might not be in a significant, might not be in the same range. You have one feature which is talking in the range of 1,000. So it has values between, let's say, 1 to 1,000, whereas you have another feature which has value between 1 to 10. So if you just put them as it is to the learning model, the learning model will not understand what it's trying to make sense out of different numbers, whereas it's in very large of something and very small of something. There are some models which will work fine with it. I think decision trees would work fine. I don't know, might work, but there are several models. Most of the models won't work well with it. Neural nets, particularly, they look at each and every data coming in as within a certain range, and then they are trying to learn weights on top of those. You want to build something which is within a certain range. So often we normalize it to a 0-1 block, but we're not fixed to do that. Being somewhat in the same range is all that's needed, so that your model is not going to be biased by some piece of information just being so high, whereas some piece of information being so low. Integer features, mostly when we have access to integer features, they are categorical. So in the case of text, as we saw, when we were putting it as a sequence, we were representing each and every word as an integer. So using integer features, we have different methods. One is to map them to embeddings. One is to if the integers are coming in a different like range, you want to normalize them maybe to a floating point number. So as I said, like if I have a value between 1 to 100, and it's an integer value in most of my cases, it's always an integer value, let's say between 1 to 100. For the learning model, I can reduce it down to a 0-1 block and represent it as a floating point. So integers are not much different from floats, but often should be normalized. Okay, yeah, so I'll quickly go over the develop model part, and I think these two will be for next class then. But once we have the features, we want to develop a learning model. And when we say we want to develop a learning model, we want to learn a function which takes in a certain kind of input, emits out a certain kind of output, and we want to correlate, we want to make that output as good, as close to the truth as possible, right? So very basic example can be y is equal to x plus b. This is sort of the equation of a straight line, right? You have y is equal to mx plus c. So if these are all numbers, then if let's say it's a 2D plane, right? And you have y as your coordinate on the y-axis, whereas x is your input. A straight line would mean y is equal to mx plus c. And you want to learn what is m, what is c, like the slope and the intercept. So if you are talking in a straight line. Whereas if you take it into multiple dimensions, as we will go over neural nets, you are going to learn sort of vectors. But in general, what you're trying to say is that some function might exist. You don't know what it is, but you have a lot of data that goes through that function and generates a certain result. You want to learn that, right? So you develop different models. The one thing in models is selection. You want to select which learning model do you want to be using. And that's the first intuitive step in the process of training and learning model, that you don't know which model is the best. There is no fixed answer. There's a theorem called no free lunch theorem that says that there is no mathematical definition of the best machine learning algorithm. Right? It's an algorithm which will always lead on to a good result. So you don't have a fixed answer. What you want to do is use your intuition and experience to boil down to a reasonable set, and then identify the best approach. Even if you are limited to just one particular kind of algorithm, you may have different variations which will be a part of it. So the process generally is that you select a model, you train and evaluate, and then based on the result that you get, you try to reason it. Okay, this sort of makes sense. Yes, I have certain improvement, and this is something that is good enough to learn. And maybe then you try another model and you observe those results. So this is there is no fixed definition to how this model takes place. In the space of neural nets, once we are dealing with neural nets, we'll try to mostly define the problem in a certain way that some families of neural nets can be used, and then we do tuning within that. So these are just some examples, but which leads on to hyperparameters. So hyperparameters are certain characteristics of the model that you choose. So these are not the things that are learned. When I was saying that we want to learn something in the model, those are called parameters. Whereas when you select a model, you have some information in that choice that you're making. You want to select a neural network, a deep learning model. You want to say, what are the number of layers that this model has? Does it have 2 layers, 3 layers, 4 layers, 150 layers? What's the size of this model? What are the number of hidden features per layer that you want? So I'm talking more in sense of neural nets because that's what we are going to cover, but different algorithms have different hyperparameters that have to be set before you actually go into the process. What is the learning rate? Which means what would be the way in which you will go on to update your model? Are you going to look at the difference between the reality and the prediction and just going to make large updates? Or are you going to make small updates? What is the rate at which you will learn? So learning rate is another important hyperparameter. which we'll cover later in the process. Okay, so should I do these in the next class or? Okay, yeah.